All right, so moving right along, continuing with antiderivatives, we're going to get into something called definite integrals. And I know last class or last lecture, I've mentioned it a few times. I said there's two types of integrals, right? You have indefinite integrals and definite integrals. So in this section right here, I'm going to slap 5.2 and 5.3 together because they incorporate the same thing, which are definite integrals. Now remember, you had indefinite, which means they weren't defined. It was just we had some, that was the integral sign, right? And then this is f of x dx right here. So remember, integrals just mean take the antiderivative of this specific function, right? We're doing the reverse of deriving. Definite integrals, though, slightly different in that they have limits. So if you notice, we have this a to b right here. What does that mean, right? Like when you're actually finding or computing a definite integral, what you're doing conceptually or like graphically is you're finding the area under a curve, any kind of curve. Okay, so like let's say, we have this curve right here, and this is a and b. These are normally x values right here, but again, it could be y values, z values, any kind of value. What determines that is this right here, this dx. That means with respect to that specific variable. So if we were computing the integral of this right here, the area under the curve, meaning this stuff right here, that stuff in blue, we would figure that out by taking the integral of that, or the definite integral. So the area under the curve from A to B, because we have to have some defined region, is this integral right here. So if the area that you're trying to figure out is above the y-axis, right, that would make sense for it to be positive area. If we had stuff beneath, like say if I had, some weird looking curve right here in the purple, like this area right here, we would have a negative area because that's beneath the y-axis. And then just like above right here, I said we would have positive area. And of course, it's completely possible to have a graph where it does something, like it goes like this, and they say this is A and this is B right here. And yeah, if you had to figure out the area from A to B, this chunk would be negative and this chunk would be positive right here. So in this case right here, you may think, oh, it's going to balance out to zero. Well, it just depends on your curve, right? Yeah, this looks kind of symmetric, right? But in the end, it just depends on what the curve is right here. This is just an example. So yeah, you can have mixes and matches of where it's just solely positive area, solely negative, or a mixture of both. It just depends again on what your function is, what's the interval that they're asking you to compute the area from. Now, before we get into, working out problems with numbers and stuff, we need to talk about an important theorem with this, and it's the fundamental theorem of calculus. So THM, of course, that just means theorem, okay? So what does this say, the fundamental theorem of calculus? It says if f is continuous on some interval AB, Notice it's included, right? Because we have brackets. Then the integral from a to b of f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So if you notice, it's the upper limit minus the bottom limit when you're computing these antiderivatives out, or you're finding these definite integrals right here. And there's some properties that go along with this. We kind of saw a couple of the properties as we were working out problems from 4.9 when we were talking about the general antiderivative, right? Now the first one says, oh, if we have a to b, we're trying to find the definite integral from a to b of c dx, where c is a constant, right? C is a constant right here. Then your answer is just c times b minus a, like this. And we'll work one out like this in a couple minutes, and you'll see that it always works out the same way. You don't have to memorize this rule. If you just remember how to take the antiderivative and evaluate the limit and evaluate these respective limits, you'll always get to whatever this is right here. The second one I mentioned before from the last section, let's say we're adding up, right? Or subtracting multiple expressions, right? So if we have this integral from a to b of f of x plus or minus g of x dx, you can split it, right? It's okay to split stuff when it's connected via addition and subtraction for integrating. So we can say, oh, this is the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So again, it's okay to split if it's plus or minus, separating those types of expressions. But remember, if it's multiplication or division, you can't split it up like that. Only for addition and subtraction. The third property says, okay, well, what if I have some integral of c times f of x dx? And again, c is a constant. What you can do is you can just take the constant and throw it out in front of the integral, okay? So all I'm doing is I'm just moving it from here, basically out in front of the integral. Nothing else in the problem changes. Did you have to do that? No, you could have left it right here and worked it out the same way. It's just that you're always, in the end, whatever you wind up doing, keeping the c here or moving it out here, you're going to wind up multiplying it into your antiderivative at the last step anyway. So it's up to you. And another property that you can use, but it's very uncommon that it pops up, is that let's say I have this integral from, again, a to b of f of x dx. If you throw a negative sign out in the front, doing so, that reverses the order of your limits. So this is just a technique that's rarely used. It's just something that is possible. Again, if you notice, I threw a negative out in the front, but in doing so, I had to change the order of the limits of integration. Again, this is a very uncommon property that isn't used too much, but it does happen sometimes. Now, how do we work out these types of problems, right? What do we do? How do we do it? So let's say we have this, let's try this out, like -1 to 2 of x cubed minus 2x dx. So really important with these problems, we're going to work them out the same exact way that we did 4.9. It's just that in the end, we're not going to have a plus c. Remember, plus c we had when we had indefinite integrals, because we were creating a family of curves, right, or a family of functions that satisfied that initial antiderivative. We weren't bound by anything. But now that we're bound between two numbers, we're actually going to get a finite answer. So we're not going to have a plus c in this case. So how do we do this? Well, this is just basically from that second property, right? We just integrate this piece and this piece, or we take the antiderivative. So what is the antiderivative of x cubed? That's just 1/4 x to the fourth. And then moving on to the second one, right? This is minus 2x squared over 2, or just x squared. And then for the notation for evaluating, usually they put like a big bar and they'll put the upper limit and the bottom limit like that. Remember, how could you check this right here? How could we check whether we took the antiderivative correctly? Well, it's because if I take the derivative of this, I should get back to here, right? Which is true. 1/4 x to the fourth. If you derive that, you get 4 over 4 x cubed, which is 1x cubed. This one right here. What happens when you take the derivative of x squared? You get 2x. So we know we did that correctly. But we're not finished, right? We're evaluating. What does that mean? We have to evaluate this with these two numbers right here. So remember, it's the upper limit minus the bottom limit. How do you do that? Well, you're just going to dump in that number. Oops. So this is the upper limit, right? This is us throwing 2, and then you have to subtract the entire bottom limit. Remember, when you subtract that bottom limit, make sure you put the entire thing in parentheses, okay? Because a lot of people will only apply this negative to the first term. No, you have to subtract the entire result. So make sure you put that, and watch the signs. This is -1, so -1 to the fourth minus -1 squared. Again, don't forget these parentheses when you subtract that entire bottom limit. So now take your time with evaluating, right? 2 to the fourth, this is 16. This is 16 fourths minus 4 minus. Inside right here, we get 1/4. 1 to the fourth is not 4, right? It's 1. Be careful with that. And then this, what happens right here? You have to do exponents first. So -1 squared is 1. With the negative, you get -1. Now we keep going, right? This is 4 minus 4 right here. Minus, what's 1/4 minus 1? That's -3/4. These get knocked out, right? And then you're left with a positive 3/4. So what does that tell us? That tells us the area under this particular curve is 3/4 from x equals -1 to 2. Now I say area under the curve, but how does it apply to real world? Well, in engineering classes or in thermodynamics, for example, the system, the way you calculate the amount of work done, the amount of heat expelled, things like that, that's done through integrals, definite integrals like this. Not as simple as these right here, but again, the concept of it. It's the concept of, oh, that's what the integral gives us, or the antiderivative. It's telling us the amount of work that the system's doing, or the amount of heat it's expending. So this is a very, very important concept or tool. Now, what if we have this, like 1 to 9 of the square root of x dx? Again, we're trying to evaluate this right here. There will be no plus c, right? Because the second you have numbers there, you're not going to have a plus c. So how do we evaluate or integrate a radical? What do you need to do? Convert it into exponential form, right? This is the integral from 1 to 9 of x to the 1/2 dx. And then we can go out there and basically do the power rule for integrals. This is still 1 to 9. And this is x to the 3/2 over 3/2, right? I don't need this right here. Evaluated from 9 to 1. Remember, it's x to the n plus 1 over n plus 1, right? So 1 plus 1/2 is 3/2. And you have to divide by 3/2. And there's a trick, right? Whenever you had like something weird over a fraction like that, the trick was to take this and just flip it, right? This is 2/3 x to the 3/2. And then now it's evaluated from 9 to 1. So it looks a little easier to work out. Now, as far as evaluating, since this is just 2/3 times this one term right here, we could say, oh, that's 2/3. And then the upper limit would be 9 to the 3/2 minus 1, right, to the 3/2. You can work like that, or you can just use it 2/3 twice. So we can say 2/3 and then 9 to the 3/2 minus 2/3, 1 to the 3/2, just like that. It's still the same thing, right? Up here, if I distributed this 2/3 and you would get the same thing, right? This times this is that, this times this is that. It's up to you as to how you want to do it. Now, how do we compute this, right? What is 9 to the 3/2 power? Well, remember, when you have a fractional exponent, that's a root, right? This is the same thing as saying the square root of 9 cubed, right? Or like 1 to the 3/2 is the square root of 1 cubed. Well, what is the square root of 9? 3. What's 3 cubed? 27. What about this one? What's the square root of 1? 1. What's 1 cubed? 1. So now we ultimately have 2/3. And then we saw 9 to the 3/2 is 27. Minus 1 to the 3/2 is 1. So you get 2/3 times 26. And that just gives you 52/3. So no decimals, okay. Only reduce it if there's a common factor, right? Like if this was 52/2, or there was some common factor that we could reduce it from here, then do so. But there is nothing that we can reduce, right? There's no common factor but between 3 and 26 besides 1. So that doesn't help. So this is your final answer right here. Remember, with the roots, convert to exponential form, right? Whether you're deriving or taking the antiderivative. And don't forget this, right? When you have a fractional exponent, something raised to a fractional exponent, the denominator is the index of your root, the numerator is the power that you're raising it to. So you go out there and you take whatever the root is of it, and then you apply the exponent. What about a trig function? Sine of theta, d theta, we're integrating from pi over 6 to pi. Well, what's the antiderivative of sine of theta? Don't forget, it's negative cosine of theta. Remember, especially with the trig functions, be careful, right? Remember, the derivative of sine is cosine, and the derivative of cosine is negative sine. Now, how do we check to see whether this is correct right here, whether the antiderivative of sine is negative cosine? Remember, if we take the derivative of this piece, we should get back to here. We do, right? First of all, what's the derivative of cosine? It's negative sine. But if I have a negative out here already, a double negative gets you back to a positive sign. So this is correct right here. A lot of people make the mistake of saying the antiderivative of sine is cosine. No, the derivative of sine is cosine. The antiderivative of sine is negative cosine. But you can always check, right? Derive this answer. You should get back to your original expression. So let's go out there and plug in these values. We have negative cosine of pi. Watch the signs, right? So this is the upper limit minus the bottom limit. So we're going to have minus a negative cosine of pi over 6. Be very careful with that, right? Because that's going to become positive. What is What's cosine of pi give you? That's -1. So you have -1 plus. What is cosine of pi over 6? No decimals, okay? Remember, with these trig functions from the unit circle, there's only a few different types of values you can have, like 1/2, square root of 2 over 2, square root of 3 over 2, right? It's got to be one of those right there. Make sure you know the unit circle, right? Cosine of pi over 6 is the square root of 3 over 2. So ultimately, what is the answer? So no decimals, okay, especially with stuff like this right here. If you type in cosine of pi over 6 into your calculator, it's not going to spit out root 3 over 2. It's going to give you some decimal answer. But we can simplify this a little bit, right? This aspect of it. This is 1 plus the square root of 3 over 2. This is your final answer. This is how you type it in on WebAssign. This is how you would leave it. We're never going to ask for decimals when it comes to trig stuff like this. All right. If it does, in the rare case that it pops up, it will specify in the directions. But if it doesn't specify in the directions, you need to leave it like this right here. That's exact form. Putting decimal is not going to be exact. All right. What about this right here? So we're multiplying right here, right? If it was addition or subtraction, we could just go out there and separate them individually and work it out. But like I said before, with multiplication and division of integrals, you can't just say, oh, it's the integral of this times the integral of this, or the integral of something divided by the integral of something. No, you can't do that with multiplication and division. So what can we do? We have to somehow, I guess, get rid of the multiplication aspect, and we can by foiling, right? Just FOIL this thing out. So when you do that, you get u squared. This is still 0 to 1 that we're integrating. U squared, and then minus u minus 6 du. I already did the outer and inner and combined that, right? You get -3u plus 2u is -1u, like that. So now everything's separated by addition and or subtraction, and we can go out there and integrate this straight across. Antiderivative of u squared is 1/3 u cubed minus 1/2 u squared minus 6u. And then we're evaluating this from 1 to 0. Remember, it's the upper limit minus the bottom limit. So we're going to have 1/3 times 1 cubed minus 1/2 times 1 squared minus 6 times 1. So remember, that's the upper limit, and then minus the entire bottom limit, right? Or the entire expression evaluated with the bottom limit. So that's 1/3 and 0 cubed minus 1/2 0 squared minus 6 times 0. Well, what's nice about the bottom limit is it all disappears, right? Because that's 0. So that was easy right there. It's just this that we have to work out. So 1/3 times 1 cubed, that's just 1/3, right? Make sure you're doing exponents first, then multiplication. This is 1/3 minus 1/2 minus 6, and then minus this 0 right here, right? Now, this is 6 over 1. How are we going to combine all this? Just LCD, right? Like you'd say that's 6, 6, and 6. This is going to be 2 over 6. This is 3 over, oops, what am I doing right here? This is going to be 3 over 6, and this is going to be 36 over 6, right? 36 over 6 reduces back to 6. 3/6 reduces back to 1/2. 2 over 6 reduces back to 1/3. And then, of course, we have this minus 0 that we're carrying along. Or you don't have to carry it since it's 0. So we get 2 minus 3 is -1. right? Minus 36 is negative 37, all divided by 6. So there is your answer, right? And then minus 0 doesn't change it right there. So again, when we're multiplying or dividing multiple terms with the integrals, we cannot just split them up like we could with the addition and subtraction integrate. You have to sit there and manipulate it or use other techniques, which we'll learn about later on in terms of how to go out there and solve those. So here we go. We have like a division thing, right? And I just mentioned we can't say, oh, it's the integral of the top divided by the integral of the bottom. So we have to kind of manipulate it, right? Just like with the last problem, we had to FOIL. Well, with this one right here, we're not going to FOIL, but we can divide, right? We can divide the bottom into everything up top. Like we're going to have this and this right here. Remember, you must divide the bottom into everything. Do not sit there and go, oh, this into that and be done with it. So if you need to expand that out, write it out so you can see, oh, I'm saying v cubed over v to the fourth dv plus, and then 3, I'll move that constant out in front of this respective integral, and then have v to the sixth over v to the fourth dv, just like that. This is legal, right? If I add these two fractions back up, what do you get? Back to here. That makes sense. Let's continue to simplify this thing. This is equal, the first one, we're not integrating yet, we're just simplifying. We still have the integral from 1 to 2 of 1 over v dv this time. And the second integral reduces to v squared dv, right? So v cubed at the top, v to the fourth on the bottom, it's always upper exponent minus bottom, right? So we're going to have a v to the first left on the bottom. Right here, we're going to have a v squared left up top. Now we can take the antiderivative of these two pieces. So what is the antiderivative of 1 over v to the first? This is a special one, right? Remember, like, if you have 1 over x to the first, or 1 over any letter to the first power, it becomes the natural log, right? That's the antiderivative of that. It's the natural log of the antiderivative of, I'm sorry, it's the natural log of the absolute value of x in that case, right there. How can we check that, right? Remember, what's the derivative of natural log? It's 1 over x, right? That's how you check that every single time. But that was a special case right there. So with this one, it's going to be the natural log of v, absolute value of that evaluated from 2 to 1, plus 3. And then what's that? The antiderivative of v squared. That's 1/3 v cubed evaluated from 2 to 1. Now, if we wanted, we could have just put this evaluation thing at the very end and do both together, right? Because they are the same limits, okay? So we can see that these reduce out, right? This goes, and let's plug in all these numbers, right? Like we have natural log of the absolute value of 2 minus natural log of the absolute value of 1. That's the upper limit minus the bottom limit. Right here, we have plus, and then v cubed, right? So we're going to have 2 cubed. That's the upper limit minus the bottom limit. But what does all that equal? Be very careful with natural logs, okay? If it's not something nice, don't simplify it. So something not nice is a decimal. If you type an ln of 2 into your calculator, you're going to get a decimal. So do not write it as a decimal. It's still ln of 2. Natural log of 1 is something nice. So this is 0 right here. So we don't need that. And then we have plus 2 cubed. That's 8. And then minus 1. So what does that equal ultimately in the end? Natural log of 2 plus 7. This would be your final answer right here. Again, no decimals. With the natural logs, how do you know if it's something nice? Just jam it into the calculator. If a nice whole number comes out, like 0, 1, 2, 3, 4, 5, then yes, reduce it. But otherwise, if it spits out a decimal, you leave it in its natural log form because we want exact form right there. Don't forget this though, okay? Anytime y'all have the antiderivative of 1 over x to the first, or 1 over any letter to the first, it's the natural log of that letter. And again, you can check that, right? Because if I take the derivative of this, right, the derivative of my antiderivative, I should get back to here, right? Which we do. All right, so now we have the integral from -5 to 5 of e dx. This is a constant, right? E is a constant right here, right? That's a number. It's 2.71, blah, blah, blah. So what's the antiderivative of a constant? It is just that constant times x. Remember, how do we check this? What's the derivative of ex? It would just be e, right? Like if this was 5 dx, or I'll just say 7 dx, the antiderivative of 7 is 7x, and the derivative of 7x would be 7, right? Same thing right here. Don't get this confused. Don't think e is a variable. It's not. It's a constant. So now we can evaluate this. We can say e, and then the upper limit minus e with the bottom limit, like that. So this is 5e plus 5e, which gives you 10e. Please don't forget, I'm going to say it again because people keep forgetting. E is a constant right here. It is not a variable. All right, this one. X to the e plus e to the x. They just basically reverse it, right? But we can still figure out the antiderivatives of these. Remember, e is a constant, right? It's not a variable. So how do you derive this? This is just the power rule right here. It's going to look a little weird, right? You're going to have x to the, remember, what does the power rule for antiderivative say? It's x to the n. If we take the antiderivative of that, it's x to the n plus 1 over n plus 1. Your n here is e. It's just the number, right? So it's going to be e plus 1 over e plus 1. Remember, there's a constant. If this was x to the 9th, you would say 9 plus 1 over 9 plus 1. This, again, e is a constant, right? It's 2.71 something. So it would be like 2.71 blah, blah, blah plus 1 over 2.71 blah, blah, blah plus 1. But do not put a decimal. Leave it in an exact form. So that's the first chunk. What is the antiderivative of e to the x? Remember, that was another little special case, and it's the only function in math whose derivative and antiderivative are the original function, such as e to the x. And now we need to evaluate this from 1 to 0. So it looks a little wonky, right? How are we going to do it? Well, we're just going to plug the numbers in, and this is going to look bad regardless because it's e, right? We can't do anything with that. So if we substitute the upper limit in, what do we have? We have 1 to the e plus 1 over e plus 1 plus e to the first, right, minus the entire bottom limit evaluated at 0. So this is 0 to the e plus 1 over e plus 1 plus e to the 0 power. Remember, you're subtracting the entire bottom limit. Now, as far as simplifying, what can you do? 1 to the e plus 1. What is that? It's nothing nice. So guess what? It's just 1 of the e plus 1 over e plus 1. And then we have plus e to the first is e. Now, what happens with the bottom limit? Be very careful right here because I know some people want to say, oh, it's all 0. No, it's not. This first one is 0 because 0 divided by e plus 1 is 0. But what's something raised to the 0 power? That's 1. Now, can we take this a little further? We actually can because 1 to the e plus 1 over e plus 1. If you take 1 and raise it to some number, doesn't matter what that number is, right? Like, what's 1 to the 5th? 1, 1 to the 1000th, 1, 1 to some decimal. It doesn't matter. It's still 1. This is equal to 1. You can throw that into your calculator, okay? Say 1 to the e plus 1. I'm sorry, the whole thing will be 1. No, never mind. Scratch that because it's just going to be 1 to the e plus 1 over e plus 1. The most simplifying we could do in that case is just say, hey, 1 to the e plus 1 is just 1. Because 1 raised to anything is just 1. But it's still e plus 1 on the bottom. We still have this plus e. And then this becomes minus 1 right here. So it is a nasty looking answer, but unfortunately, that's as much as we can do. Let's try another trig one. All right, so with the trig functions, remember that when they seem kind of difficult, but the trick is to think of, oh, what function can I take the derivative of that will bounce me back to this? So what trig function can I take the derivative of that will get me back to this right here? Well, it's just secant theta. So that, remember, the antiderivative of secant theta tan theta is secant theta. Why? What's the derivative of secant of theta? The derivative of secant theta is secant theta tan theta. So now let's go out there and evaluate. We're gonna have the upper limit. Not secant of theta, it's gonna be secant of pi over 4, upper limit minus bottom limit, secant of 0. So what are secants of whatever, right? Or if you get cosecant or cotangent of some weird or of some value. Remember, if you have troubles evaluating this, go out there and rewrite it in terms of sine and or cosine. Remember, secant is 1 over cosine. So this is like saying, oh, what's 1 over cosine of pi over 4? Now it doesn't look so bad because we should all know what cosine of pi over 4 is. This is like 1 over cosine of 0. So what is cosine of pi over 4? That's the square root of 2 over 2. So we have 1 over square root of 2 over 2 minus 1 over, what's cosine of 0? 1. Now, what happens with this? Remember, when you have that fraction divided by a fraction, we can take this and bring it up top by flipping it. So this is 2 over root 2 minus 1. And we're not quite finished with this one yet. Why? Because we have a root and a denominator. Remember, you have to rationalize the denominator. So remember how you do that is you just multiply top and bottom by whatever that denominator was. So we get 2 root 2 over 2, which is just root 2 in this case. So your final answer is square root of 2 minus 1. Again, no decimals, right? No decimals. We want exact answers. All right, if we try this one out. So we have multiplication, right? What do we do in this instance? Because we can't say the integral of this times the integral of that. So we got to break it apart. How are we going to break it apart? Multiply, right? Before we do that, though, we need to change or alter one piece, and that's this, right? What should we do with this? Convert it into radical form. I'm sorry, exponential form. And then when you do that, now we can distribute, right? So 4 times t to the 1/2 is just 4t to the 1/2. What's negative t times t to the 1/2? Remember, this t to the first. What do you do with the exponents when they have similar bases? You add the exponents. This is minus t to the 3/2 dt. Now let's go out there and integrate. What's the antiderivative of t to the 1/2? Remember, it's going to be t to the 1/2 plus 1. That's 3/2 over, again, 3/2. I still have that 4 out there. And then minus, moving on to the second piece, what's the antiderivative of t to the 3/2? Well, it's t to the 3/2 plus 1. So that's t to the 5/2 over 5/2 again. And we're evaluating that from 4 to 0. Of course, we're gonna let's clean up these fractions on the bottom of these other fractions, right? How do we do that? Remember, it's just you're gonna multiply these, right? We're gonna bring them up and we're gonna multiply by the reciprocal. So we actually have 4 times 2/3 t to the 3/2 minus 2/5 and then t to the 5/2. And we're evaluating that from 4 to 0. Remember, upper limit minus bottom limit. So we're going to have 4. Well, actually, not 4. We're going to have 8/3, right? We can multiply that through. We're going to have 8/3. And then we're going to have 4 to the 3/2 minus 2/5, 4 to the 5/2, and then minus the entire bottom limit, right? So we're going to have 8/3, 0 to the 3/2, minus 2/5, 0 to the 5/2. Please don't forget, right? When you are evaluating that bottom limit, you subtract the entire expression. Make sure you throw parentheses to remind yourself, oh yeah, we need to distribute that negative in. In this case, we're okay though, because this is all just a big old 0, right? What about these right here? Remember, fractional exponent means radical, right? What does 4 to the 3/2 really mean? That's the same thing as saying the square root of 4 cubed, right? Remember, the index is your denominator of your fractional exponent. What's this one right here? 4 to the 5/2 is the same thing as saying square root of 4, but raised to the fifth power. So what's the square root of 4? 2. What's 2 cubed? 8. What's the square root of 4? 2. 2 to the fifth is 32. So keep going, right? We have 8/3 times 8 minus, and then we have 2/5 times 32 minus this whole big 0 right here, right? And then where do we go from here? This is 64/3 minus 64/5. And of course, we're going to sit here and figure out, we can combine this into one fraction. All right, so how do we do that, right? With this calculator, we can do it pretty easily, right? You can say 64 ABC, that's the fraction button. Let's see. 64 ABC fraction button. And then minus 64 ABC 5. If you notice, it said, oh, it's 8 and 8 and 1/5. I'm sorry, 8 and 8/15. It gave us a mixed number. We want an improper fraction. How do we convert this to an improper fraction? Well, once you already have the answer displayed right here, you're going to press second and you're going to press the ABC button again. If you notice, it says in blue, it says ABC to D over E like that. So you got to press the second key first and then the ABC button. And it's going to convert it to an improper fraction for us. So you get 128 over 15. So again, the key is using that ABC button right there. No decimals either, unless it asks for it, which it most likely won't in this case. So at the end of this section, I'm just going to give y'all a few more antiderivatives that may pop up, kind of like the trig ones that popped up, or that can pop up. I'll just call this additional integrals. So you may not necessarily see them in this section. They may come up in future sections. They probably definitely will. And in your future math courses, they definitely will at some point as well. So like with the hyperbolic stuff, for example, the antiderivative of hyperbolic sine is cosh or hyperbolic cosine of x. And notice I'm putting the plus c right here. Why? Because we don't have limits. These are both nice because there's no sign flippage. And another important one, this one's probably more important, is if you have an exponential, so the x is in the variable and a is a constant. So again, how could you check all these, right? How could we check whether we found the correct antiderivative of this respective expression? Well, if you derive these right here, you would get back to the left-hand side. That covers it for this section.